All right, let's get into it. You know, inside pretty much everything you own, your phone, your laptop, even your coffee maker, there's a hidden language being spoken. It's a language made of circles, zigzags, and lines that tells electricity what to do. So today, we're going to learn the basic alphabet of that secret language.
Yeah, I know. It looks like a total mess, right? Like some secret agent's code or a chaotic map. But stick with me, and I promise, by the end of this, you're going to look at a diagram like this and see the pattern, the actual story being told. We're going to crack this code together, one symbol at a time.
You know, when you learn any new language, you don't start with poetry. You start with hello and goodbye. It's the same thing here. We're going to start in a perfect, imaginary world. Think of it as Electronics 101. And our very first word is the idea of a perfect power source. This is the foundation for, well, pretty much everything. And boom, here it is, our very first symbol. Just a simple circle with a plus and a minus. This little guy is what we call an ideal voltage source. You can kind of think of it as the powerhouse, the engine that gets everything moving in our circuit.
So what's the big deal with ideal? Why do we call it that? Well, imagine you have this magical water pump. It gives you perfect, constant water pressure. I mean, it doesn't matter if you turn on 1 sink or 10 sinks or a fire hose, the pressure is always the same. It never dips. That's exactly what an ideal voltage source is. It makes a promise to deliver a certain voltage, and in this perfect little world, it keeps that promise, no matter what.
And this graph just shows it perfectly. So you've got voltage going up and the current being used going across. And look at that line. It is perfectly, totally flat. What that's telling us is that even as you ask the circuit to do more work, to draw more current, the voltage doesn't even flinch. It stays rock solid. That's what we mean by perfect, unchanging, ideal.
Okay, that perfect world is super useful for understanding the basics, but let's be real, we don't live there. The actual batteries in your phone or your TV remote, they are definitely not perfect. So, it's time to get real. Let's see what happens when we bring this idea back down to earth.
Okay, take a look at these two side by side. On the left, there's our perfect, ideal source, just a circle. But now look at the right. This is the practical or real-world version. See that new little symbol, that zigzag thing? That, my friends, is the game changer. It's called internal resistance.
And that little bit of internal resistance, that is the imperfection of the real world all in one symbol. You can't get away from it. Every real battery, every power supply has it. It's like a tiny bit of friction that gets in the way of the electricity. And you've actually seen this. Ever start your car at night and see the headlights dim for just a second? That's the battery's internal resistance at work. The engine is drawing so much power that the battery's voltage takes a tiny dip.
This chart just lays it all out. Our ideal source is a champ. It's always giving you 100% of what it promises. But the practical source, the moment you actually plug something in and put it under load, it loses a little steam. It can't quite deliver 100% because some of that energy gets lost fighting its own internal resistance. It might seem like a small drop, but trust me, in the world of engineering, that little difference is a huge deal.
All right, so we've got voltage down, that's our electrical pressure, but what if you don't really care about the pressure? What if what you really need is a steady, constant flow, like a guaranteed amount of electricity per second? Well, for that, you need a whole different kind of source.
And here it is. Say hello to the ideal current source. Now, at first glance, it looks a lot like our voltage source, right? It's a circle. But look closer. The key is that arrow inside. That arrow is your big clue that we're talking about flow, a constant directed flow of current.
Let's go back to that water pump analogy because it works so well here. If a voltage source guarantees pressure, a current source guarantees a specific flow rate. It's like a pump that says, I will give you exactly 1 gallon per minute, period. It doesn't care if the pipe is massive or super tiny, it will automatically adjust the pressure, which is the voltage, to make sure that flow stays perfectly, absolutely constant.
And, no surprise here, just like our voltage source, the current source also has a real-world, slightly less perfect twin. But check this out, the imperfection is different. See how the internal resistance here is parallel to the source, not in a line with it? What that means in the real world is that some of the current kind of leaks away through this internal path. It's like having a tiny hole in your pipe. Not all the water makes it to the end.
All right, so we've talked about the things that provide the power, the active components. But what about the things that control it? Let's talk about the most basic, most fundamental passive component out there, the part that's all about managing that flow of power.
This little guy is a resistor.
So on the left is what one actually looks like, in the real world. And on the right, there's its symbol, that zigzag we've seen a couple of times now. And that zigzag shape isn't an accident. It's supposed to look like a difficult, bumpy road. It's a visual way of saying this thing puts up a fight and resists the flow of electricity.
So, what decides how much it fights back? Well, it's just pure physics. Let's go back to our trusty pipe analogy. It's way harder to push water through a really long, skinny, rusty pipe than it is to push it through a short, wide, smooth one, right? It's the exact same idea for electricity. The type of material, how long it is, how thick it is, all of that adds up to determine its resistance.
Okay, so far our power sources have been, well, kind of dumb. They just put out a set voltage or a set current, and that's the end of the story. But where electronics gets really interesting and really powerful is when components can start reacting to each other. So let's level up and look at some smarter sources.
Everything we've seen so far that's in a circle, those are what we call independent sources. A good way to think about them is like the outlet in your wall. It provides power, but it has no idea and it doesn't care what you plug into it. But there's this whole other category of sources that are way more aware, way more dynamic.
And here they are, dependent sources. The first thing you've got to notice is the shape. It's a diamond, not a circle. That diamond is a dead giveaway. It's the symbol for smart. The job of this component is to look at the voltage or current somewhere else in the circuit and then create a brand new voltage or current somewhere else based on what it sees. This is the absolute core concept behind stuff like amplifiers, how a tiny little signal from a microphone can control massive speakers.
Okay, let's put it all together and look at this again. I know this might have looked like spaghetti before, but now you can actually start to read it. You can spot the independent voltage source over there on the left, right? You see the resistors, those zigzags, and look, way over on the right, there's our diamond. And you know what that means now. That's a dependent source. It's listening to what's happening somewhere else in this circuit and reacting to it. See? The whole story is starting to come together.
So let's just quickly recap the big ideas. We've got the ideal, perfect world versus the practical, real world, which always has that pesky internal resistance. We know that active components provide power, and passive components, like resistors, control it. And the big one, we can tell the difference between the simple, dumb, independent sources, the circles, and the smart, reactive, dependent sources, the diamonds.
And just like that, you've learned the basic alphabet of electronics. For real. You can now look at the blueprints of the tech that's literally all around you and start to understand the conversation that's happening inside. You've got the decoder ring. So the only question now is, what are you going to read first?